Okay, hello.
Oh, you understand? Yeah. Simon is
Behold,
supposedly.
the great venerable I/O API. I'm sure you're all intimately familiar with it.
Oh, hold on.
Read, write, seek, what more do you need? And if you were designing an interface for controlling a magnetic tape or a hard drive, this makes a lot of sense. You might say this is the natural interface for controlling a disk. But these days, when you call these functions, you're not really controlling the disk. In fact, the disk probably can't even tell that you've done anything. That's because sitting in between you and the disk, there's a layer called the page cache. Page cache is an in-memory mirror of your file system. Whenever you load data in from disk, that data gets stashed in the page cache, so that the next time you access it, you don't need to bother the disk. And when your system starts running out of memory, the operating system finds something that you haven't accessed in a while and evicts it. So the page cache accelerates your reads and accelerates your writes. Not only that, it coalesces your writes and makes your SSD last longer. So the page cache is really a brilliant thing. So what happens when you call read? Well, assuming the data you're trying to read is already in the cache, all that happens is a memcopy. The kernel copies the data out of the page cache into your buffer. And when you call write, it's just the same thing in reverse. It memcopies the data out of your buffer into the page cache. No I/O happening, really. The I/O happens later in the background, whenever the kernel decides to synchronize the page cache with the disk. So, yeah, read and write, maybe a natural interface for controlling the disk, but that's not what they've been doing for a long time. These days, read and write, they don't manipulate the disk, they manipulate the page cache, and perhaps they're not the natural interface for that. So, today, we're going to be talking about file-backed memory. By the end of the talk, you should know what it is, when you should use it, how it works, and most importantly, how to use it safely from Rust without introducing undefined behavior into your program. Oh, and I should say, questions. If anyone has any questions, please ask away anytime. Brandon will find you with the microphone. Okay, first though, I want to show you something. So I've got a file here full of historical price data from the Korean Stock Exchange. It's a very simple format. It's just timestamp, 8 bytes timestamp, 8 bytes price, timestamp price. So it's just a bunch of data points. And I've written a little thing for browsing this data. So here you can see. Here's the price changing over the course of a day. If I zoom in, you can see the individual data points from the file. There's one day. There's the days either side, a week, month, a couple of months. You can see it's loading the data in from disk as we scroll around. Keep going. But I think you get the idea of what this thing does. Data goes back to 2019. We can zoom in. Anyway, this is the AI boom, by the way, making the Korean economy go crazy. So that file has 2 billion data points in it, and I assure you my crusty old laptop is not rendering 2 billion circles. So the way this works is I take the visible part of the x-axis and subdivide it evenly into 10,000 points. And then for each of those timestamps, I look up in the file to find the point nearest to that timestamp. And that gives me a 10,000 point subset of the file, evenly distributed across the visible part of the x-axis. And then I render those circles. So pretty simple, and it works very nicely. But you'll notice there's one part of the story that I skipped over, which is I said that for each of those timestamps that I want to sample at, I look up in the file and find the data point that's closest to that timestamp. So how do I do that? Anyone got any?
Binary search?
Yeah. I hear binary search. That was quick. Yes, binary search. The points in. Oh, we've got a question. The question was if we have a bunch of sorted points and we want to locate one of them by timestamp, what's a good way to do that? And the answer was binary search, yeah. If you've got sorted data, then you can't really do much better than binary search. And it's even provided for us by the Rust standard library, so that's nice. However, the implementation of binary search in the standard library is a method on slices, and we have a file. So, first thing we need to do is load the file into memory. So here I'm calling fsread on the path. That gives us, that reads the contents of the file into a giant vec of U8. Next, I'm using the zero copy crate to cast that slice of U8 into a slice of points. So here I've got a struct down here defining the format of the file. It's just what I said before. 8 bytes timestamp followed by 8 bytes price. And this zero copy thing here, at runtime, this has no cost. It's just like an alignment check. You don't have to use zero copy or byte marker. I'm just being lazy. You can do this by hand. It's not that bad. Okay, and so once we have a slice of points, we can call binary search by key to look for the timestamp that we want. And then this line underneath here is just saying we don't really care if we found the exact timestamp we were looking for. We're just looking for a point that's close to it. Okay, so this works. What don't we like about this? Right. Gigantic whopping vector. This is going to read the entire file into memory. That file that I was showing you before with the 2 billion prices in is 30 gigs. So that means if we implement it like this, then for the whole time that you have the price browser thing open, it's going to be consuming 30 gigs of memory, which is not good even if you have 30 gigs of memory. And if you don't have 30 gigs to spare, then what's going to happen? As you load in the file, the system's going to start swapping out the start of the vector. So you're reading it in from disk and then like writing it back to disk, even though it's already on disk. It's going to be a nightmare. So ideally, we would like something which runs in constant memory. So let me I'm going to expand the implementation of binary search over there on the right. We have lower bound and upper bound, and each time we go around the loop, we query the midpoint between the two bounds and to find out whether we can refine it left or right. It doesn't matter so much. But the point is that we query the midpoint here by doing a an array index into our giant slice of points. We can replace that with something which reads a single point from the file at that point. So here, in the setup, all I'm doing is opening the file. And now, every time we need to read a point, we create a 16-byte buffer, and we call read exact at, which is the Rust word for pread. So that just reads 16 bytes in from the file, and then we cast it to a point. So this also works, and doesn't use tons of memory. Great. What don't we like about this?
You need NVMe to run it fast.
You need a fast hard drive.
Lots of random reads.
Lots of random reads. Yes, that's true. I mean, if we're binary searching, then that's kind of shogunai. Yes.
Too many syscalls, I guess.
Okay. Yes. We'll get to that. I'll tell you what I don't like about it. It's messed up my code. Like, it used to be really simple, and now we used to have like the I/O happening here, and then we had like the logic of our algorithm here. Now the I/O is all mixed in with our logic. This is bad for composability. It's really bad for testing. Like, it's hard to test code that does a bunch of I/O inline. Yeah. And this isn't even that bad, right? Because we know, in this case, we know the amount of data we need to read in, 16 bytes every time. But anything where you're, consuming a dynamic amount of data, like if you're writing a parser or something, I don't know if you've experienced the pain of, you're parsing something and then, I've reached the end of the buffer. I need to stop and refill the buffer and retry. It can really make your code a lot more complicated. So I've got one more implementation to show you, and no prizes for guessing what it is. We mmap the file. This gives us a slice of U8. And then I cast it into a slice of points, and actually the rest of the code is exactly the same as the first implementation I showed you. But unlike the first implementation, this doesn't immediately load the entire contents of the file into memory. In fact, when we call mmap here, it doesn't do much at all. All it does is it tells the operating system to mark a region of our address space as file-backed. So what does that mean? Normally, when you write to a bit of your address space that you haven't written to before, the operating system will scurry off and find you some RAM to use as the backing for that bit of your address space. And normally, it'll find some nice fresh RAM full of zeros. But if you've told it, if you've marked that region of your address space as file-backed, then instead of private zeroed RAM, it'll find the memory which the page cache is using to cache the contents of the file and just map that into your address space. So when you read from that memory, you're reading directly out of the page cache. And when you write to it, you're writing directly into the page cache. Question?
That assumes that the file was already in the page cache?
Yes, assuming the file was already in the page cache. If it's not, then what happens is the first time you read from a region of the slice, the kernel will intercept the load and populate the page cache quickly behind the scenes.
With 30 gigs of...
No, just with the one page that you're accessing.
Okay.
So just the 4 kilobytes, or 4 kilobytes and maybe some either side, depending on how it's feeling.
So then how big is your point slice?
So
Is it like magic virtual memory, not actually 30 gigs?
Right, so the point slice is covering 30 gigs of your address space. But the data doesn't actually materialize until you try to read from it.
Because it's only a reference anyway. It's not like there's actually like an array.
There's no...
Or something like that. Yeah, okay.
It's a slice, yeah. Yeah, so exactly, it's the magic of virtual memory. It appears to be a slice completely populated with the contents of the file, but in fact, the data is only being loaded in on demand as you look at it. Right, and this is the secret of how I could write that price browser thing in like 60 lines, and it performs well enough to view a 30 gig file. So, shall we look at some benchmarks? Here's the first version. Unsurprisingly, the setup time is proportional to the size of the file. This 600 milliseconds per gigabyte is basically measuring the read speed of my SSD. But then once the contents are loaded into memory, assuming you can load it into memory, the query times are very fast. Yeah, I mean, so you can see, well, you probably can't see, but like even at 30 gigs, this is going to be like a millisecond to do the whole 10,000 queries to assemble the sample. So you can do that every frame, no problem.
Alex, what are the axis labels? It's quite small. Can you read it? Like, what's the x-axis
The
on the first graph?
X-axis on all three graphs is the size of the file.
Okay.
First graph is the setup time. So you can see it's just, you know.
Okay. Yeah. The y-axis is on is the label at the top.
Yes. So the y-axis in all three is milliseconds, but
okay.
you can't see the numbers probably.
Did you like generate different size files just to measure this and generate this graph?
I used that one giant file, but I just loaded prefixes of it.
Okay.
And yeah, this benchmark is the time to assemble that 10,000 point sample with it completely zoomed out. Yeah, you can see the query time has this interesting kind of logarithmic staircase shape, which comes from the way binary search works. Yeah. So that was the first one.
One more question.
Yes.
There is this really interesting logarithmic, which is, as you said, binary search is logarithmic.
Yeah.
But there are these, especially in the hot query time, there are these steps.
Yeah.
Do you happen to have an explanation?
Yeah. So binary search needs to do a certain number of probes, like a certain number of midpoint accesses, which is going to be the ceiling of the logarithm of the size of the file. Right. So every time the file grows more than a power of 2, the number of probes jumps up by 1. So those are so you can see every time the file size doubles, we gain a little step. And then the fact that it has a linear component, I think, is just probably not able to make as good use of caches and that kind of stuff. All right, so the second one, the one where we just use pread to read one event at a time, one point at a time. The setup time is now instantaneous because we're just opening the file. All of the slowness has moved into the first query that we run. But then the second time we do a query, it's kind of pretty fast again, because now, although we haven't buffered anything in user space, the contents of the file at that point are now in the page cache. So at this point, when we're doing the hot queries, every time we do a pread, it's just mem copying from the page cache into our buffer. A couple of things to notice. One is, even when the file data is all in the page cache and we're doing the hot query, the per probe cost is much higher than before. And I think someone mentioned it, right? A lot of syscalls. So previously, every time we were looking up the midpoint, we were just doing an array index. Now we're doing a read, which is a syscall, which is a lot more expensive than indexing an array. The other thing to notice is even in the cold query time, when it is having to load file data in from disk, it's still quite a lot faster than the first implementation, like 3 times faster. That's because the first version loaded the whole file in, even though we're not going to read the whole file. Right? We're sampling 10,000 points out of 2 billion. There's a bunch of data in there that we're never even going to access. This version, where we're just reading in the events as we need them, apparently only needs to look at like 1/3 of the file. And if we zoomed in on like 1 day, this would be much more extreme. Okay, last one. Mmap. Setup time, again, instantaneous. And then the query time, again, all of the I/O is happening the first time we run the query. But then once it's hot, notice the performance is now exactly the same as the version 1, the fully in-memory version. Because once again, every time we probe the midpoint, we're not having to do a syscall or anything. It's just an array access, just like the first one.
Alex?
Yes?
Can you go back 2 slides? I just want to see the per probe on. Okay, it's 7 microseconds. Okay. Okay.
Yeah. The data's a bit funky, right, for the mmap. My simple model is not capturing whatever this shape is. I don't know. I'm not sure why.
So that's it, right? Mmap just works.
Mmap is, yeah, it's the way to go. Yes, question. Oh, microphone coming.
That way the recording will pick it up.
For some of the slides in your line of, the red line of best fit that I'm guessing, why do they take the lower bound of the scatter plot and sometimes they don't take the lower bound of the scatter plot?
I'm trying to take the lower bound always. The reason is, I mean, I find that this is a good way to model benchmark data. So like when if something takes 10 seconds for your computer to run, then sometimes it's randomly going to take 11 seconds. But it's not randomly going to take 9 seconds. If it takes 10 seconds to do it. So when you're benchmarking, you get like the floor is real. But then above that, you get loads of noise. So I find this is just a good way to analyze benchmark data.
And on the last line, why does there seem to be like 2 distinct lines?
Yeah. It's bimodal, right? There's two ways that it can go somehow. I was actually getting that. I was getting some, like, all 3 of these were really bimodal the first time I ran the benchmarks, and I was trying to figure out what was causing it, and I eventually pinned it down to address space layout randomization. So like depending on how the code of my program was getting loaded into the address space, it could either be fast or slow. It's crazy how big of an impact address space layout has. So I turned off layout randomization, and it fixed the first 2.
My guess would be the bimodal reason for hot query is just cache misses. Like it's just like there's a page cache that was evacuated by another query, and I had to load it back in, and so it adds this bimodal kind of situation when that happens. That's the first thing that comes to mind.
This guy is also leaning on the page cache. Yeah, maybe I forgot to turn off layout randomization when I did the third, when I did this slide. I don't know. Any other questions? Okay, so hopefully you're all sold on wanting to use mmap for your programs. How do we do it? Well, I'm going to be using my favorite crate again, Rustix. It's pretty easy. We just open the file. I want to mmap the entire file, so I get the length, and then pass them to mmap with there's some flags that you can pass to control its behavior and so on. And the operating system picks an empty bit of your address space to use, maps the file there, and then gives you back a pointer to the start of the region that it's mapped it at. Now, we don't want a pointer, we want a slice. So we call slice from raw parts with pointer and length. And there we go, we're done. But slice from raw parts is an unsafe function. What does that mean? So all functions have preconditions that you have to satisfy in order to call them safely. Like, for example, a function assumes that its arguments are laid out a certain way in memory. And that's what the type signature is for. The type signature tells you the preconditions and postconditions of the function, and the type checker ensures that the preconditions are all satisfied, otherwise it doesn't let you call the function. But sometimes a function has complicated preconditions that can't be expressed formally in the language of the Rust type system. And in that case, you have to express them informally in the language of English via extensive documentation. And of course, the compiler can't read this, so we have to be the type checker. So what are the preconditions for creating a slice, specifically a slice of U8? Here's my attempt to summarize it. The memory that we're going to create our slice from must be allocated, initialized, inert, and exclusive. So let me try and explain what these are. All Rust values must live within an allocation. And slices are no exception to that. Now, it doesn't have to be a heap allocation. Of course, it could be a stack allocation, or they could live in registers or static. Even consts and literals count as allocations according to the way that Rust uses the term. But what you can't do is grab a random bit of free, unallocated memory and make a slice out of it. If for no other reason than the allocator might decide to use that memory in the future, and like some random stuff is just going to show up in the middle of your slice. So if you want to use some memory, you have to make sure you allocate it first. When you create a new allocation, the bytes of that allocation are uninitialized until you write to them. And it's fine to have uninitialized bytes floating around. You're just not allowed to look at them. So you can't read from them. But it's not a problem to have them per se. Like, for example, if you have a struct, the padding bytes between the fields there's no way to read those from safe Rust. So you can leave those uninitialized and it's fine. But we're creating a slice of U8. Every single byte of that is readable from safe Rust. So we need to make sure that the whole, all of those bytes are initialized before we make a slice out of them. Okay, another thing that the Rust compiler assumes about allocated memory is that it's inert, meaning you can read from it and write to it, and that doesn't have any side effects. Like the compiler wants to elide redundant reads and writes, and it doesn't want that to be observable when it's eliding those. And then finally, I'm saying that the memory has to be for the exclusive use of the slice that we're creating from it. So that means that if we're making a mutable slice, then all writes to this memory, so long as the slice exists, all writes to this memory have to go via the slice. And if we're making a shared slice, then there better not be any writes to this memory at all. Like, it had better be immutable. So, how are we doing on... I said that this file-backed memory is literally mapping memory that the page cache is using to cache the file contents. And when somebody writes to the file, they modify the page cache memory. So that means if we create a shared slice and some other process writes to the file, our memory is going to change. So this is illegal even for even if we made a mutable slice, but it's very, very, very illegal if we've made a shared slice. Those aren't supposed to change. So that's a fail. Next, if we write to our slice, suppose we make a mutable slice and then we write to it, well, we're writing into the page cache. So that means we're actually changing the file. So that sounds like a side effect to me. So this memory is also not inert. Calling mmap is considered to create an allocation. And just on a practical note, the allocator is going to avoid this region. So this is allocated memory according to Rust. And it is also considered pre-initialized. Like the contents of the memory here are well defined. They're just the contents of the file. So we're actually good. Oh no, sorry. We're good on initialized. Spoiler. mmap does create an allocation, but remember that files that can shrink as well as grow. Like someone can truncate the file. And we've mapped the file into memory with a certain length. That was the length of the file at the time that we mapped it. If someone truncates the file, then the end of this memory gets deallocated. So, and if you try to read from it, you get hit with sigbus and killed. So it is initially allocated, but it may become deallocated if someone else truncates the file. So, I mean, the core of the problem is that file-backed memory is shared memory. Because anyone else that opens the file can see what we've written, and they can write to it themselves. And they can even truncate it and deallocate it for us. And just to really illustrate the point, have a look at this. So we mmap the same file twice. And then from each of these slices, we can take a mutable reference to the first byte and pass them into this function. So these two mutable references, they're pointing to different addresses. But those addresses are backed by the same physical byte of RAM. So the first time we call assert eq, it passes, of course, because they are the same byte. And then we add 1 to the byte. We do it by writing through y, but we could also write through x. It's the same. And we assert that they're equal again, which of course they still are, because they're still the same byte. And when we run this, it works. But then when we run it in release mode, we get this goofy panic message claiming that 1 does not equal 1. You can probably see what's happened here. The optimizer looks at this and says, well, they used to be equal. We added 1 to one of them, so they surely aren't equal anymore, and replaces the check with an unconditional panic. And this is classic consequence of undefined behavior, right? It works when you run it in debug mode, and then you turn the optimizations on, and you get something different and very goofy. So the sad conclusion is that the semantics of mmap are not compatible with Rust slices. So what are our options? We can use read volatile and write volatile. Those are fine to use even with crazy memory, that has side effects and things. But that's not good. That's no way to live. I mean, at that point, you may as well just go back to using pread. Occasionally, you can actually prove that the file is immutable, and then it's fine to mmap it. But that's pretty niche. Like, it's not very often that you come across files protected by fsverity. And then option 3, the most common option, is to just do it. And this is actually, it's okay, especially if you're distributing binaries yourself. Like, you can compile it and then test the actual binary that you're going to be distributing to make sure it doesn't do anything crazy when the file changes. You know, that's okay. But you definitely can't do this in a library, right? You can't make a library that wraps mmap in unsafe and then exposes it through a safe interface and then throw that up on crates.io. Then your library is just unsound and no one should use it. Not pointing any fingers, mmap3. Okay, or fourth option, maybe we can change the semantics of mmap. Right, let's talk about file systems. Simplifying greatly, the main job of a file system is to map regions of files to blocks on disks. So here I've represented this file by its path, but actually files are not identified by their path, they're identified by a numeric ID called an inode number. And if I unsimplify this picture just very slightly, you can see it's a two-step process where first the file system maps the path to the file, and then it maps regions of the file to blocks on disks. And one thing that this enables is you can have multiple paths pointing to the same file. So then calling open on either of these files has the exact same effect, opens the same file. This is called hard links. You can also have a file with no paths pointing to it. The most usual way that you get this is if you have a file open and then someone deletes it, it doesn't delete the file while you have it open, it just deletes the path. So you can continue reading and writing the file, and then when you close the file system will clean up the inode and free the blocks. But you might not know that you can actually create files in this state, right? So you can create a file without giving it a name. You do it by passing this flag called oTempFile.
666
That's the permissions. Yeah, readable by Satan alone. Yeah, so you pass this flag, oTempFile, very badly named. There seems to be a law with Linux that anything called temp file must have nothing to do with temporary files. And quoting from the man page, it says that it's for creating a file that's invisible, which you can then populate with data and then link fully formed into the directory tree. But I put it to you that a file with no path can't be opened by any other process. And a file that's never had a path, you know for a fact that the file descriptor you got back when you called open is the only file descriptor which references that file. So the only way of modifying the contents of that file is through this file descriptor that you have here. So I propose that mmapping such a file is actually safe. It's impossible for any other process to. So we open the file with this flag, we mmap it, and then we drop the file descriptor. So at this point, the only way to modify the file is through the mapping that we've just created. So I think it satisfies the exclusive requirement. Is it inert? Well, if we write to this mapping, if we write to this file, that data will get written to disk. It is still a real file, but it's not observable by any other process. And I claim that a side effect that's not observable is not a side effect.
What if it's forked?
Our process?
Yeah.
I guess we can open it with clo-exec. But also, I think it's still fine. Yes, it is still fine. So a different version of your question might be, what if like another thread in our process randomly reads and writes to is writing to random file descriptor numbers, just like passing integers into write as the file descriptor. The Rust language specifically forbids that. That is, if you do that, then all bets are off in terms of safety. So I think.
Just to be clear, you're saying that it's inert because it's Schrodinger's mmap. Like you can't see the right, and that's okay. Like
I'm saying that doesn't count as a side effect.
okay.
So like if the compiler decided to elide the write because it knows that it doesn't need it or something, like it's never going to be read again. Then
because nobody else could read it anyway.
Yeah. So
if you're not going to read it and no one else can, then it might as well doesn't matter.
yeah, exactly. So it's still safe to elide redundant writes. Yes.
If you like do this too much, is that how Heisenbugs appear?
If we do this too much, is that how Heisenbugs appear?
Wait.
So I think this isn't going to give rise to any Heisenbugs. That's my hope. I think everything here is deterministic.
So a better thing would be to say, if you don't do this, is how Heisenbugs can appear.
Right, if you're doing.
Where you just use the mmap, that can cause a bug to just like happen and not be observable.
Yeah, that's true. yeah, right. So raw mmap could produce like bugs that happen sometimes and not other times, depending on how the moons align. Moons? Okay, and finally, what about people truncating our file? Well, they can't, right? You can only truncate a file if you can get a file descriptor to it. So bits of our map are never going to be randomly unallocated behind our back. Okay, so I think this is safe. It is also an empty file. So this is the world's worst way of creating an empty slice. The file that we wanted to mmap is some file that already exists on disk and has a path. Well, I have a, oh, sorry. Yeah, so we can safely make a slice from it. Well, I have a fix. We create our private file, and then we copy the contents of the target file into our private file, and then we mmap it. There you go. That's the file that you wanted. Now, you might be looking at this and thinking, copy the file. The whole point was to avoid reading in the entire file. Well, let's go back to this slide. I talked about how you can have sharing over on this side, where multiple paths share the same file. You can also have sharing over on this side, where multiple files share the same blocks. So these are hard links on the path side. When you do it on the file side, those are called ref links. And it works a bit differently. This ref links are copy on write. So if two files happen to have identical contents, then the file system can just point them at the same blocks on disk. But then if you write to one of the files, it breaks the sharing at that point. So only one of the files changes. Yeah. So this is, oh, and here I'm doing, I'm copying the file contents with std.io copy. Through the magic of specialization, this will actually resolve into a call to copy file range syscall, which will try to do this copy acceleration trick with the ref links. So just to run through how the trick is working, we start with the file that we want to mmap, ferris.png. We create a private file that no one else can access, and then we ref link the contents of Ferris into our private file, and then we mmap that. Once we're done with it, we unmap and close the file. The file gets deleted, the blocks are no longer shared, and everything is back to how it was to begin with. If someone tries to modify Ferris while we have it mmapped, then their writes are going to go to a different block. Let's see some benchmarks. Setup time is a little bit slower. It has to do this business with making the ref links and so on, but it's, you know, it's still very fast. You could mmap enough files to fill up your ulimit in a second. And then the rest of the performance profile is just indistinguishable from vanilla mmap. Okay, so I framed this as modifying the semantics of mmap. Let me just make that explicit. So we now have, so whereas vanilla mmap gives you memory that reflects the live current state of the file, our snapshot mmap gives you memory that reflects the state of the file at the point when you called mmap. I think this is actually more useful, right? Like, you get a point-in-time snapshot of the file, and you can read it in any order, you can take your time, and you get like a consistent view of the file, even if other people are changing it.
If other people do change the file, other processes do change the file, you're in like a copy on write situation, right? So would that imply that the whole file will get copied, or just the pages that have been modified?
Just the blocks that get modified.
Okay.
So
just the blocks that get modified.
yeah, so like 4K normally.
Okay.
Yeah, so that's fine.
Some other processes' performance that assumes they can have fast writes.
So it doesn't really change the performance because SSDs are actually copy on write anyway.
Okay.
What it does do is it may cause fragmentation. Like it might make the file's extent table grow a bit. Right, so that's for like the read side, but the write side is even more interesting because our writes, when we write to the slice, it doesn't change the file, the original file, it changes our private snapshot. But we can then choose to clone our changes back into the original file. Again, it's instantaneous. No data actually has to get copied around on disk. It's already on disk. And is atomic. So like if the machine loses power halfway between doing this, when it comes back online again, your snapshot will be gone. And the original file will either be completely in the state before you called commit, or completely in the state of your snapshot. I think this is really interesting, like for anyone doing kind of database-y adjacent stuff. Okay, so that was all of the good news. Now for the bad news. We've used two features to pull this trick off, private files and ref links. They are not universally supported. Okay, the two major mainline Linux file systems, XFS and Butterfs, do support both tricks. So it works great there. But ext4 doesn't support ref links. And, you know, even though they've been recommending people to migrate away from the XD family since a decade ago, there are still a lot of disks out there that are formatted with the ext4. I think it's because the Ubuntu installer still picks it as the default for like bizarre, come on Ubuntu.
You're not supposed to use
ext, no, it's,
You're meant to use XFS now.
you've always meant to be.
Oh.
I mean, ext4, like when it,
It's not a bunch of it. It's that universal installer everybody uses. I think it always recommends ext.
which universal,
Well, non-Arch or non-Nix users, there's like this GUI. You click next, 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 and you say your region.
and it gives you
And
ext4.
it gives you ext usually, yeah.
I mean,
Yeah, maybe I'm just dumb and I override it, sorry.
I mean, ext4 was when it was created, it was introduced as like a life extension to give people more time to migrate away from ext. That's like 10 years ago. But yeah, obviously it's still out there on like loads of machines. So so if you use this trick and then your users use ext4, it's still going to work. It'll still be safe, but they're going to be hit with a surprise at the start when it actually physically copies the whole file on disk. It's going to be like the version 1 where it reads the whole thing in, but even worse because it has to, you know. And then the really frustrating one is APFS, the macOS file system. They did the hard one. They implemented reflinks, but they don't support private files. So as far as I'm aware, there is no way to safely use fmap on macOS, mmap on macOS. If anyone knows of like a way to create a file that's not linked into the directory tree on macOS, please tell me.
Wasn't proc files?
Sorry?
Wasn't it process file?
Oh, so you're asking about /proc?
Yeah, you could use a process file instead of a temp file. It's on all Linux systems. Now you can create process files who are just usable by one process. Like in a command line, if you have this.
Yeah, but that's Linux, not Mac. That's Linux, not Mac.
Yeah, that's on Linux.
Sorry, on the command line, if you.
The problem is Apple. Yeah.
Oh yeah, okay.
Steve.
Oh, that thing. Okay, I have no.
Also, it has to be a real file on the same file system as the target file. Otherwise, the reflinking doesn't work. So if we created it on a tempfs or something, I think that's what you're suggesting.
In Linux, there's a procfs. So you can make a process-only visible file using a special Linux feature.
Okay, but does it create an inode on the same file system that you're trying as the file that you're trying to access? Yeah, it probably makes an inode in some funky memory-only file system, right? Or anyway, I don't know.
It's not this straightforward even for other file systems. For example, if you use advanced features of Btrfs, for example, you set it up to control hardware and use it in RAID 6 mode, it does awful things to files when you attempt to use reflinks.
Oh, okay. So you're saying there's some configurations in which Btrfs doesn't really support reflinks. Okay.
It will start copying immediately, and it might also block your process because of distribution of the flows like different devices.
Okay. Yeah, and I'm not talking about. I haven't looked into what this does on NFS or Samba.
What's on your machine?
XFS. Okay, so here's my.
In your defense, though,
Yes.
it's worth stating that, yeah, Btrfs has this problem, perhaps ZFS or ZFS, if you're British, has this issue that you mentioned as well, but all databases recommend file systems. So if you're making a data-intensive application where you need something like this, you've selected your file system, and if you haven't, you're not doing it right. You have, because there's a whole article that is related to this about how your file system matters for just random file mapping operations in general. It's very old. And they talk about this also. So I think you're doing an app like this, you better have thought about it. You better have picked your
Right.
process, I think. So you probably didn't pick btrfs.
Most databases normally they want to use direct IO, and normally they recommend XFS because it's the one where direct IO is the least funky. But yeah, yes. If you're writing software for your own consumption and you're in a position to make sure the machines are all running a modern file system, then you don't have to worry. You can be happy and use this trick. But yeah, if you're distributing software for general consumption and you don't know what file system your users are going to run and whether they've configured it in some insane broken way, then yeah.
If you owe a temp file on Mac, will it panic? Or will it just be like, okay, and then not do it? Because then it's still safe. So you can make it in the library.
Oh, right. I mean, yeah, I think you can check whether it's available, I guess. Well, I mean, you can check if you're on Mac and just refuse.
I'm saying if you're, I guess you can check if you're on Mac and just panic from your library.
Yeah, technically safe.
Okay.
Not the most useful.
Yeah, so you can put it in the library and you're like, I'm not going to hurt it.
Don't use it. Yeah. And in fact, I have put this in the library. So if you want to use it, there it is. Mmap snapshot. Yeah, here's my summary of the talk, basically. Yeah, I especially think the atomic commit semantics are really interesting. And yeah, XFS actually has a bunch of, XFS can do compare and swap. It's amazing. ext has basically no ability to do atomic anything. So yeah, that's my rant about ext over.
Unfortunately, this might die, but are you ready to do Q&A?
Yeah, I've got some more slides, but I think probably questions is better.
Yeah, so why don't we just shout, and I'll turn on my mic so you'll at least be in the video. All the other questions, not really.
I'll just flick through the other slides so they're on the video.
Do you have to mess with any of the unmap semantics at all?
Any of the
Unmap?
on map?
When you, I'm not, yeah, my memory's kind of hazy here, but I believe mmap is somewhat paired with unmap, or am I kind of just hallucinating here?
Unmap,
Using-
UNMAP.
UNMAP.
Munmap. Yeah. So when you're done with it, you have to unmap the memory that you've mapped.
And the semantics there are kind of just,
In terms of how it interacts with with the semantics of Rust, I guess that's the same as freeing an allocation.
Yeah.
So yeah, mmap counts as a kind of allocation. Unmap would be the free. Yeah.
Anyone else? Any questions? Okay, hold on. Wait for me to come with this hockey puck.
Thank you. For the fork criterion that you had earlier, why do you not need uniqueness?
Oh.
Is that is uniqueness implicit? Is that why, or?
Why did I not choose? Why didn't I pick the word uniqueness?
No. Why don't you need additionally uniqueness?
Oh, okay. What do you mean by it?
For A and B in a set R, there does not exist another A prime, B prime, such that A prime equals B prime equals A equals B.
Okay, so you're asking whether it's a condition, whether it's a requirement that this region of addresses is not mapped to memory, which is also mapped to a different region of addresses. Is that what you're asking?
No, well, why do you not need uniqueness? Is it implied or?
I don't.
Hold on. Yeah. By uniqueness, do you mean that the file itself is unique, or the contents of the file? What do you?
No, not the file itself, not the contents. The address, I guess, then?
Oh. for the address to be unique. Yeah, I'm still not sure what it means. Like,
Yeah, because mmap doesn't mmap. So first of all, we're working in virtual memory here. So you'll get an address back from mmap, which is a system call in Linux or whatever operating system. And that address that you've received is going to be unique to your process and is also a lie. And then the operating system, whenever you try and access that memory, will map that memory to the real physical address, which is inherently unique. Otherwise, it couldn't have been allocated.
So it's OS side to keep it unique.
That's right, yeah. The OS will keep track of what is and is not in physical memory.
And because it's assumed from OS, you don't need to consider it here.
I think so, yeah. And then also, like I said, the address returned by mmap is unique to your process by default because it's virtual memory. So it's a lie. It's like a fake.
yeah, although, I mean, the whole problem with raw mmap is that the physical memory that the OS has mapped is not uniquely being mapped into our into this region of our address space. It might also be mapped into other places as well, like any other process that's mmapped the same file.
Yeah.
But that's the point of the trick. If it doesn't have a path, then other processes can't mmap the file. Yeah. So it is uniquely mapped to this one range in our one process.
Thank you.
Making my way over to you.
Thank you for the great talk. So just another follow-up question to the previous question that was asked. The way I understood it is, I think it's possible to mmap the same file into multiple different regions in the address space of that single process that we're doing this in. So can you imagine a scenario where you could like shoot yourself in the foot doing that with this machinery?
Yeah, but not if you're using the trick.
Right.
Because if you use the trick, every time you mmap, it creates a new snapshot file. And we make sure that that only gets mapped once. Yeah, and then we throw away the file descriptor, so you can't map it again.
Yep, that makes sense. Thank you.
I find it really interesting that like what you set out, or at least it seems like you set out to solve this problem of this isn't like sound because we can't express it in the type system. And then what falls out is this other extremely useful, arguably more useful thing. And it's just kind of elegant. It's really cool.
I think it's like a classic Rust thing, right? Where you're fighting with the type system, and you're like twisting and contorting your program to make it fit the type system. But then when you finally get there and step back and look, what you've got is better than what you started with. Like it kind of guides you into writing better software. I think that's kind of
types are good.
Yeah,
you heard it here first.
Did you perform some system-wide profiling? Like now I wonder, will some maybe flags to mmap affect that? Because, for example, kind of f-allocate, you can pass populate flag, HTLB flag, it will warm up your caches and speed up even more?
I have a slide about map populate, yeah. So, do we have time for this kind of stuff?
Let me check. We have the space until 9, so yeah, we got time.
Okay. So, sometimes you don't want reading from an array to suddenly block and do a bunch of I/O randomly. Like, especially async people get twitchy about this. It's kind of I would say a foot gun, a misfeature with cooperative async that you have to be really careful not to accidentally do any I/O. And mmap is a great way to accidentally do I/O. So if you want things to be a bit more predictable, you can pass this flag to mmap called map populate. And what that does is it means when you create the mmap, it does actually load the whole file immediately into the page cache, like it blocks. And it also sets up the page table and everything, so that the first time you query, it's all ready to go and fast. It's not going to do any I/O. And in fact, it's even a bit faster than the in-memory version because all it's doing is populating the page cache, whereas the first version that we started with populates the page cache and copies it into user space. So we get to skip that second mem copy. Yeah, so that's map populate. That's one of the flags you can pass to change the behavior.
Any other questions? Okay. Making my way over.
This is a totally random idea, but have you considered creating something like a read-only reference that could be used in two processes by basically allowing them to both open the file, but only open it for reading? I don't know if that's possible. But that kind of mirrors how like borrows work in Rust, right? So you either have one borrow that is allowed to mutate the thing, or you can have as many borrows as you want as long as they're all reading.
Mm-hmm. I see. So you want initially to map a file as writable, write some stuff to it, and then turn it into a read-only mmap, and then give that to other processes as well?
Yep.
Should be possible. Like you can, if you keep the file descriptor around, you can send that to other processes over Unix sockets. I don't know how you can't guarantee that the other process is going to, be well behaved when it receives the file descriptor, right? Like you can't. You can if it's on tempfs, you can seal it, and then other processes can't. You know for sure that they can't modify the file, but.
I guess we can relax the constraints and say like the other process is also a program written in Rust that is using the same library. So it can have the same assumptions about the mechanics.
I don't know
if that makes sense.
If that's sound though. I don't know if you're allowed to write unsafe safety docs. The guy on the other end of the Unix socket promises.
Yeah.
But I think you can do basically what you're asking for with memfds. See also my previous talk, which you can write into and then seal, and then the operating system guarantees that no one will ever write to them again, and then you can pass those off to other processes via Unix sockets.
I think this should be possible via duplication. You can duplicate and then set flags for new file descriptor. This, at least for Linux, this should work.
But I don't know if you can make it read-only.
You need to check the flags for Cisco.
Yeah.
Yeah, gotcha. That just gave me another crazy idea, but I don't want to hog the mic. I'll find you later. Thank you.
Anyone else? Okay.
Thanks. So am I right that this is specifically for when we want to simulate having the entire block of, or the entire file in memory, and not for when you say wanted to start from the beginning? Say in the scenario where you normally would have opened it up with a buff reader and you want to just iterate, like use iterators to go some like n% through the file, and you actually don't know where you're going to stop because you don't know where your good like canceling condition is. Like it might be 5% in, it might be 80% in. Is it still just better to use buff read and just suck it up, or does this provide anything for that case?
Yeah, I mean, I would still mmap it. So you mmap the whole thing, and there's no cost until you actually start reading from it. And there's another flag that you can pass. What's it called? Madvise sequential. Right, it's on this slide. Which tells the operating system, hey, I'm going to be reading from this thing sequentially, so whenever I read from a certain region, you might want to
the next thing. Okay.
Kick off some like async read ahead.
Whereas like a naive buff reader might have been less elegant about how it actually fetched the bytes off of the disk.
Right. I guess if you're using buff reader, then every time buff reader reads, I mean, if you're reading normally from just if you're just using read, I guess the kernel is going to assume that more sequential reads are coming, and it will start loading. It will start doing read ahead into the page cache. So it should, I guess it would be about the same speed. Yeah. But I mean, buffer. The difference is that with this you can read ahead as far as you like. You get like a giant slice, right? You can. Whereas with buffer reader, it's giving you 1 byte at a time or 1 line at a time or something.
Yeah, it's like however much you ask for at a time.
Yeah, up to a certain byte or whatever.
Yeah, so I would
Probably about the same performance, I'd say.
I feel like this needs to be benchmarked, but like you said, a big benefit of mmap here is if you're not just reducing the file, and you happen to need, for instance, so there's a file format at a big company that does web tech called Google, and they have this file format called record.io, which has like a header, and this header is like a big mapping of like what's in the record. And so you read the record, they built it so that they could read, maybe SS Table does this, not record.io, I don't know. But basically they have like all these keys in the header, which fits in memory in 2003. And then they can use that to just like get whatever they want from the file. And so if you're doing something like this, mmap makes sense because like you're looking at the beginning until you're not. And then you need to get something from over there. And if you're using buff reader, that means now you've hit a cache miss immediately as soon as you've jumped. And if you jump back and forth enough times, that'll happen. And the OS kernel is almost certainly better than you or any library at caching stuff. So you might want to let it. That's my take without benchmarking, personally.
Right, and I mean, the real place where mmap shines over read is when you're going to be jumping around, but to the same places again and again, because then it's like all completely set up. Whereas with read, you'd have to be doing seek, right? Syscalls.
Oh yeah, seek, I forgot. Yeah, the fact that you have to call seek is just like the, yeah. I've never called seek.
Just read the whole thing in the memory.
Yeah, so when I worked at Google, we had like a terabyte of memory, you just always read it all in. Anyone else? Okay, because I have questions for you again. I'll repeat some of them, but they're more personal questions, so. Does anyone else have any other questions about the talk? Okay, so before I ask you, like, thank you.